So let me, so I'd like to hope, I hope at least be able to answer some questions from yesterday. So let me first start by talking about spectral networks. So suppose we have a real surface X. And suppose we're given some kind of spectral curve. Sigma inside the cotangent bundle of X. So this means that the projection to X should be a R to 1 map proper. And we're going to assume that, so let's call phi1 pr sections from some open subset of X into sigma. So let's choose, so let's choose R, locally let's choose R different sections of the spectral curve. And so maybe we're assuming that this is maybe reduced. And let's assume that we're working with the group SLR. So that means that phi1 plus pr equals 0. So what are the phi's? The phi's can be considered as one forms on X. So these are the things which we are calling A, I of Z, BZ. And if Z is a local coordinate on X. So these are holomorphic forms on X. Now, this is of course away from the branch points. At the branch points of this mapping from sigma to X, the phi's of course can interchange. So typically sigma at any point will have some kind of branching which interchanges some of the phi's, then maybe some other sheets that don't branch at that point. So as we go around the branch point, then phi1 interchanges with phi2. Stays the same. Now from the spectral curve, we get what maybe some people might call a web. We get some kind of collection of foliations. So we get some real foliations on X. These are given by the formula real part of Pij equals 0. So Pij is Pi minus Pj. So these are kind of the basic structures which we're interested in. So let me try to draw what this looks like near a point like that. Okay. So this is a little bit complicated. So roughly speaking, if we look at phi1, 2, so this is, if we draw the picture like this, real part of phi1, 2 equals 0, then this just looks like the typical singular point of the quadratic differential. when we go once around, then P12 becomes P21. P1 gets interchanged. Now there's the other foliations, it takes a little bit of time to understand what the other foliations look like. The other foliations, the other foliations look like this. So on one side of the singular point, it's just going to be a foliation. Right? This is just a form. So let's just say like so if we try to draw a real part of P13 equals 0, then it's going to look something like that. But now what actually happens is this looks like this. As you go through the singular point, the single foliation on one side of the singular point, on the other side of the singular point, it doesn't match up because the P13 and P12 interchange. Okay, so they're like. So just like a small detail when trying to picture what's going on here. Roughly speaking, we think of this foliation as just being some kind of constant foliation. Now, what's this spectral network? So a spectral network is going to be a graph on the surface. So a spectral network is going to be a graph on X with endpoints at the singular points. Now there's different types of singular points. So here we've drawn a singular point which comes from a ramification of the spectral curve. We'll also be considering in a natural way singular points which are just imposed by ourselves. So just we impose some boundary points to the problem. Okay, so those will count as singular points also. Okay, so spectral network is a graph on X. In fact, as you will see it later, I'll restrict to the case where there's no ramification. So later we won't have that kind of singular point. Later, to start with, it's a graph on X with endpoints at the singular points, edges labeled by pairs ij, and such that the edge an edge ij should be containing a leaf of the real part Bij equals 0. And then we have collision, so vertices, so plus collision.
So can you have several edges marked by the same pair of integers?
Yeah. Each edge has to have a label. And in fact, geometrically you can see what the label is. It just tells you might say each edge has to be one of these three foliations, one of these several foliations, and whichever foliation is best. There's a question of direction maybe, which I'll get wrong if I try to do it anyway, so let's not talk about that. Now, what about collision? So a collision is going to be a point where we have something like this, a picture like this, like Ij, Jk, and Ik. So just out in the middle of nowhere, not at any of the singular points, but just out in the middle of somewhere in the Riemann surface, we might have an edge labeled Ij that meets an edge labeled Jk. They'll have to collide and form an edge labeled Ik. So in this picture, this means that the foliations look like that, and like that. So let's draw like a basic picture here.
And so the point is in the middle should be a single point.
No, this is not a singular point. As I said, this is just out in the middle, no error.
So it's
Just out in the middle.
not an because
It's not a singular point. The singular point is it's kind of the origin of the curve. Okay.
Excuse me, shouldn't you also keep drawing J and GK?
Yeah, they don't need to collide. So I mean,
They give rise to the new branch, but they also, I think
Yeah.
they should also keep drawing J and
yeah, definitely. So I mean, you're allowed to do this. Okay, if your graph comes like that, and if your graph comes like that, you're allowed to collide them and create a new edge like that. You don't need to if you don't want to. This is allowed to just.
Once you've given this data, it doesn't determine the graph, and the graph's compatible with the.
Yeah.
And do you allow quadruple collisions? Do you allow multiple collisions?
That's a good question.
It doesn't have any
Generically, no, but I guess in principle, yeah. I mean, in fact, we'll see that in a minute in this FL3 case. But yeah, I think in principle, if you have SL4, SL5, or something like that, you could have several different guys that come together and sort of combine together and create one. In the sense that, I mean, multiple collisions you can think of as degenerating, as breaking apart into a union of collisions like that sort of happen at an infinitesimal level. If you write down multiple collisions that looks like that, if you zoom in on this point, so to speak, you could think of as a combination of collisions like that, then that's going to be allowed. Okay, so let me just draw our standard example. So our standard example is where for the group SL3. So this is the spectral curve that looks like that. A threefold covering of X with two branch points. So we draw the two branch points like that. So I guess what I should have said here is that I said the endpoints are the singular points. There's a more specific condition, which is if the endpoint is one of these singular points, then the only ledges that you're allowed to start from that point are supposed to be labeled by that pair of indices ij. A singular point corresponds to a generic simple ramification point corresponds to a pair of indices that get interchanged. And the edges of the spectral network that start at that point are supposed to be labeled by those two vertices. Okay. So at this ramification point, we're going to have two indices that label, and at this ramification point, we'll have two indices that label. And so it took us some time to computer drawing and so on to figure out what the picture looks like, but this is what the picture looks like. So the spectral network consists of any of these rays starting from these points, but a possible graph here would be, let's draw this in blue. A possible graph is that you start at this point, you take this edge, you start at this point, you take this edge, and then these two edges collide, and they create an edge like that. So this blue thing is a possible spectral network.
Can I just ask, what happens for R equals 2? Can anything happen?
For R equals 2. So for R equals 2, no, for R equals 2, there's not very many spectral networks. In particular, there are no collisions.
Yeah.
So that's why we're interested in R equals 3. That's why we're starting with R equals 3. In case R equals 2, which I discussed a little bit last time, there's not any collisions because you can't have ijk. Okay? So it just means, in the case of R equals 2, a spectral network is just consists of a leaf, some segment in a leaf of foliation. I guess that's kind of instructive for the thing we'll be discussing next year. So
is it an empty graph, the spectral network?
No, it is the critical graph of the quadratic differential. Just no collisions.
Because it's
empty graph, I don't know about that. We'll see in a minute, I mean, what my object over the empty graph coming out. That might be a trivial object. Yeah, you are. But so now let me discuss. So in the case, for the case R equals 2, we had what was called saddle connections. So these are leaves of foliation that connect to singular points. For R bigger than or equal to 3, for any R. So this is Gayoto-Moransky terminology, called this a BPS state. So I'm not sure, I think in other papers maybe they call them generalized saddle connections or something like that. I have no confidence whatsoever in that would be interested in learning anything possible about this as to why this corresponds to what you call BPS states in physics. So I can't answer that question. But there should be something related to physics. So this is the terminology of Gayoto-Moransky. But what does this mean? It means it's just a generalization of the notion of saddle connection, which is to say it's a spectral network which is finite and has all its endpoints at singularities. Okay, so in this picture, for example, we can see that this blue thing is not one of those unless we happen to put another singular point up here. Okay. This blue thing, we've got two lines that collide, but then they go off and create some lines that goes off to infinity. So we can try to draw a picture. So, I mean, if we take the same picture, but we just kind of assume that there happens to be a singular point up here. If this happens to be a singular point of the IK foliation later on, then that would be a BPS state. And you can just imagine all sorts of complicated pictures where you kind of if you have enough singular points in your foliation, then that can create a kind of arbitrarily complicated BPS state. Maybe we'll just be calling these things spectral networks themselves. Sorry? No, so we'll see that in a minute. Well, I can draw. I mean, there's a. This is an important picture. It can look like that. And then the thing that happened here is that this hexagon in the middle can actually turn to a row as you like. So you can have family possibility. Let's see. So let me just make a brief comment which relates to what I was saying yesterday, which is that the existence of these guys this guy, that's the obstruction to genericity for yesterday's construction. So, you know, when you have a WKB question, we kind of made a simplification. We just kind of assumed that our matrix was already diagonal, so that these forms, that corresponds to having sigma be split into our different sections. But in general, when you have a WKB question, then you have a spectral curve. And that defines you a spectral network. And our proposed construction of a pre-building, which depends only on this collection of differentials phi. The proposal is that this will exist and have the right properties if the spectral network does not have any of these DPS states in it. That's just kind of a comment relating to yes at the top. So, now what do we want to do today? So today we'd like to discuss how these are related to stability conditions. Okay? And I should say, one big question I have is why there would be any relationship at all between WKB theory and the question of stability conditions. Maybe Maxime will have something to say about that, possibly, or something, or not. I don't see you. I think it would be great to understand why. Maybe we should understand the physics more closely, or something like that. Anyway, let's go. There does seem to be some relationship. So what about stability conditions? So the idea here is that we're going to make some kind of limiting type of proprietary category. Where we fix a fiber. So where the fiber category is sort of over a point in the base is some kind of proprietal category of the cotangent fiber at that point with coefficients in the with base points the spectral curve at that point. So for example, for the case r equals 3, then sigma x is 3 points inside the cotangent fiber at our point. The cotangent fiber at our point is the complex plane, and so the proprietal category of the complex plane with coefficients in with respect to 3 points, 1, 2, 3, is supposed to be, as they tell me, the A2 category. And then, according to the other option I was talking about yesterday, you might, instead of looking at this cotangent fiber with respect to these points, you might then go at 1 dimension higher.
I'm sorry, do you have some lambda-Wilkins? What do you think here? I mean, what do you think?
Probably, but you should probably ask the expert about that.
But what do you mean by parasitic?
Just some category where there's Lagrangian. So the Lagrangians here are very simple. There's only 2 points. And the Lagrangians are basically just segments connecting those 3 points.
You say it's exactly A0?
Yeah, I think so. If you choose 2 of these points, you choose 2 of these segments, that usually the equivalent. The kind of category of Lagrangian branes inside the complex plane with endpoints on those 3 points is supposed to be the right category that equilibrium are right there. Should know
Shouldn't set contact between
well, there's another thing we can do, which is the Calabi-Yau 2 category associated to this guy. That's the thing you get by taking this conic vibration with singular points over these points. But the No, this guy is not a quality-out category. That's what I'm saying. The technique to make it into a quality-out category is to, which again I don't understand, but so they tell me, is to replace this cotangent bundle by this thing I was calling Z yesterday. There's a three-dimensional variety mapping to the cotangent bundle, which is a general libraries of P1, and the P1 breaks into two copies of P1 over the spectral curve.
So probably this is the one.
This is this is going to be the one that has a quality out structure. Okay, so you can, there's some kind of modification, which is A2CY2. I think apparently for what we're discussing here, there's not too much difference between these two cases for the question of stability conditions. Also, sorry, I said it yesterday, but I should say this is work with Lunel, Bobby Hyden, and I mean I think it follows quite closely a kind of more general philosophy of we're just kind of like looking at some example of that philosophy. So
what does link X?
that means a point in the base.
Is it on this?
Well, yes or no. So we make a vibration whose fiber over any point is this category. And then now we would like to look at space of section. So
What happens over the branch points?
I'll get to that in a minute. That I can say something about. So over the branch points, over the branch points, you mean like this? I'm not sure we actually know. I think Fabian seems to be able to say something at sometimes, but we're not completely sure. So this is actually supposed to be a perverse Schober with some non-trivial spherical functors at these branch points. We don't know the details of that. As you'll see, then we're not even going to talk about branch points anymore. Okay, so we get this family of categories where something's happening over the branch points, which we're not completely sure about. We get this family of categories over the base X, and we would like to look at the Fukaya category with coefficients. Okay. This was the other question from yesterday, which I'll try to answer now. So, modulo this question of what's the spherical functor at the endpoints. What's the Fukaya category with coefficients? So this is a category whose a Fukaya category whose objects are pairs G comma A, where G is a graph in X. With endpoints at singular points.
Singular points of
So the singular points, there's two different types of singular points. There's either the branch points, or we just impose some singular points, some endpoints. That's what we're actually going to be doing in a minute.
So it also depends on sigma, or it only depends on X and Y.
No, the singular points are part of the data of X. I mean, you think of X as being a pointed frequency.
Singular points of G.
No, the graph G is allowed to have other singular points, which I'll explain now. But the endpoints of the graph should be at the singular points. In the sense that, I mean, this is really supposed to be a perverse Schober here. And so the graph could be anything you want, but you want a section of the perverse Schober over the graph. That makes it so that if the graph ends at some point, then that point has to be a singular point, otherwise it wouldn't be a section of pixel length. And the case where we take a pointed Riemann surface is really going to be a case where we sort of do an extension by zero across that point of this perverse Schober, essentially. So it sort of says that the section along that point, along that edge, is allowed to do anything at once at the end point. And then there's going to be some more complicated condition at these singular points, which corresponds to saying, the Fukai, the section of the Fukai category should be a brain that sort of stops at the ramification point. I should also, this is completely work in progress. So I should actually really say work in quote progress. Okay, so I think that sums up the situation pretty well. I might say a different way of saying that is that I guess Maxime is probably going to be able to give a fully general theory of this. We're just working on a single example. And it's not clear whether we'll be able to do our example before Maxime does the general theory. But anyway. But let me just say what these things are. So the category of the objects are G comma A, where G is some kind of graph whose endpoints are at the singular points. And let's think of trivalent. Okay. It can have higher valency vertices, but you should really think of those, for the algebra, you should think of those as divided up into a sequence of trivalent vertices. Now what's A? So A is now a section of the script A of the family of categories over the graph. Okay. So I think this was partially treated already in this paper by Kaponov and Checkman. Oh, Herbert Stoker.
So you say P is a section of this curly, what is curly?
Curly A is this family of categories. For each point at the base, we have this product category. So it means that for each point in the graph, we're supposed to be giving an element of this product category. So pictorially, it's kind of not so difficult to understand what's going on pictorially. Pictorially, you just have to think of drawing the spectral curve, but in its fully dimensional realization. So the base is a two-dimensional thing. Then the spectral curve is some kind of ramified cover of the base. Draw that. Some kind of ramified cover of the base. Then we're going to fix some segment, which, for example, ends at the ramification point. Then there's going to over this segment, we'll have two different sheets of the graph, and the typical section is just going to be for each point of the graph, the segment that joins the two sheets together. And that segment is going to be a point, and that segment is going to be an object in this category of the divider. So basically the objects of this A2 category are generated by shifts of objects denoted 1, 2, 1, 3, and 2, 3. 1, 2. So we'll call this little a and little b. And kind of the describing feature of this category is that we have an exact triangle. So basically this A2 category is just a category, it's like the smallest category you might say, that has an exact triangle like that. But the point here is that these objects correspond to the labeling by pairs of indices 1, 2, 1, 3, 1, 2, 3. That label, you might say the kind of observation here, the origin of this subject, I guess, I don't know. The observation here is that labeling works out perfectly well with the notion of spectral network. It's the same set of labels as the spectral network. So you might say that's kind of the original observation here. So the labels that you have on the spectral network are the same as the labels you have for objects, for the basic objects.
And what is the relation of ij and ji? isn't just a sheet?
Yeah, maybe. Well, I mean, there's a very complicated to understand your question about direction of stuff on these graphs. If you switch the direction, that corresponds to a shift. So if you switch the direction back, you might have shifted by 2, depending on the direction your object, your edges need to be given orientation in sort of the universal cover of the orientational bundle. Okay, so, but now let me just get to really the key point here, which is that what happens at a tridimensional vertex of the graph G. And that's what's corresponding to a collision. So the tridimensional vertex of G we're going to have, so let's call this E1, E2, E3. Let's orient them this way, and this way. So we're going to have associated to these edges. Well, what I should say here is that the first condition for being a section is that A of X is independent of X inside some edge E. The value of the object is the same on all points of an edge.
But they all do some different things.
There are some different categories, but the categories are really the same because along an edge which doesn't go through a singular point, these are all the same categories, just C with respect to 3 points. So there's some kind of connection on this family of categories in some way. But anyway, the main point here is that we have objects A of E1, A of E2, and A of E3. These guys are all going to be objects. We can all push them by this connection into the fiber category over this point. And the point is that we need to have a triangle. So at the prime vertex of G, we have a triangle. An exact triangle. This is in the fiber category over that point. You can draw this geometrically. It's not completely easy to understand. We tried to draw this picture on the blackboard in Andy Netsky's office one day. So it's a little bit difficult to understand if you think of this picture here. But let me just say, and this is Maxime's philosophy of this limiting stability condition. That something like this is supposed to give us a Lagrangian in the total space of this vibration. So in our case, for example, it's supposed to give us a Lagrangian in the total space, which is the cotangent bundle of X relative to the spectral curve. How is that going to work? Well, you can try to think of drawing this. So, over a tridimensional vertex downstairs, we're going to have these 3 points. We're going to have this family of stuff, which is 3 points at each of these curves. We can just think of this as being constant. So upstairs, we're going to have these 3 points, and over this edge, we're going to have one of these segments. Over this edge, we're going to have another of the segments. I might have gotten the direction wrong here, which would be important, but sorry about that. Over this edge, we're going to have another of the segments. And in the middle, we're going to have these segments all joined together to make a triangle. Then we need to fill in that triangle by kind of a Lagrangian brain in the middle. And if you think, I can't reproduce it here, but if you think about it a little bit more, you can see that actually as you approach this point, the Lagrangian really lies over something that looks something like that, basically. And as you move into this point, these little segments are actually curving into the middle. So at the midpoint, it's really going to be 3 lines that meet in the middle. And then you have to try to understand, try to imagine, depending on where you are in this picture here, how you get a curve kind of thing there. But it does seem to work out that you can kind of draw a Lagrangian that you can get by filling in a segment here, a segment here, a segment here, filling in some way over that point. Then there's an idea, so this, Simpson explains very nicely in his 2016 string math talk, which is that if you try to define the Fukaya category, where you take some limit where the size of the fiber, now Maxime's here, they can tell me, the size of the fiber is getting really big or really small?
Small.
Really small, okay. The size of the fiber gets really small. Then in the limit, the Lagrangians are going to look like this. So, of course, before you take the limit, if you have a fibration, there's no reason that a Lagrangian total space should look like something fibering over a Lagrangian in the base with fibers that are Lagrangians in the fiber. That looks like it might be an easy way of getting a Lagrangian, but in general, a Lagrangian is going to be different. And we can see this happening here, very close to this point. But the idea is that in a limiting sense, that is actually going to happen. So then now we're just looking at kind of the combinatorics that are generated by that kind of a theory. But the combinatorics are actually kind of easy to understand in some way. We just look at graph, and then a section just means over each edge of the graph, we need to specify an object. And when we need a trigonal vertex in the graph, we need to specify a triangle. The morphisms here in our you have to pick some directions for notation and so on. In this notation, the morphisms go in this direction. And since the way I like to think about this is that let's just draw these vectors, okay? This is the E1 vector. This is the E2 vector. This is the E3 vector. Okay. So in terms of vectors, the morphisms go from here to here, here to here, and then from here to here. That's going to go from the E3 vector back to the shift of the E1 vector. So that's why the map from E3 to E1 goes from E2 to E1 shifted by 1. Now, let me just say the more precise version of what's going on here. So you need to define, we don't have the definition, but we're trying to think about how to do the definition correctly. In order to correctly do the definition, we need to understand more closely what's an exact triangle in a triangulated category. This is kind of interesting. Right? Maybe before I get into that, I should just say that the case of a spectral network, is the case, so if you have a spectral network, you get one of these things. By plugging in on the edge, you plug in the object here that corresponds to the labeling that we had for the edge. And the condition of the collision, where's my collision? The condition of the collision exactly says that we have an exact triangle in the fiber category. So the case of the spectral network is going to be the case where these objects over the edges are themselves stable objects in the fiber category. And at a vertex, they fit into their standard exact sequence. Now, what should you do? What kind of algebraic conditions do you need to say? What you really need to say is what's an exact triangle in a pre-triangulated DG category. So let me give a definition here, which is so there's going to be an A infinity type of definition, which apparently, according to Feynman, is maybe due to Paul Seidel, possibly, or maybe for that. But we can actually give a sort of a strict version. So strict version. So this was something that I didn't know until just a few months ago, which is, you might say, a great, I'm sure you guys will think this is a great lacking on my part, but anyway, that's something you guys already know this for the past 35 years. But what's an exact triangle, okay? So when you think of an exact triangle as being something where this guy is isomorphic to the cone on these guys and so on. And of course these morphisms should compose to 0. But that's, so what it turns out is that we shouldn't just say we want these morphisms to compose to 0. We should actually give the homotopy that composition to 0. So what's an exact triangle? It's that we have an object A, so I'll just call this ABC. We have like morphisms maybe U, V, W, and so on. These are those shapes. But then we're also given morphism from A to C. Let's call that H. Let's call this like K. Let's call this L. And we would like D of H equals V composed with U. D of K equals W composed with V. D of L equals, let's just call this U again. It's the shift. Okay, so that doesn't really say anything new. But however, so this is kind of the key point that you need to understand, which is that when you want to actually describe a triangle in a kind of a precise way, you should make an additional condition. And you can think, if you think about it, it's not too hard to see that this condition is satisfied if you make C be the cone on A and B. Okay. So what's the condition? It says, well, we have two different ways of making a map from A to A itself. Okay, so we can take W composed with H, or we can take K composed with U. So you know H and K and L are morphisms of degree -1, right? Because D of these guys are morphisms of degree 0. D of these guys has to be that, so that means that these guys are morphisms of degree -1. Okay. So if we do something, if we do these two maps, we get morphisms of degree -1 from A to A of 1, but that's the same as the morphism of degree 0 from A to itself. And the condition is that this plus this should be equal to the identity of A. And B plus the other one. There's three. Of course, there's three conditions like that. And then, as far as we can tell, we also want to add the conditions like L composed with H equals 0.
So should it be equal to identity or
No, it's equal to
to identity?
That strict version says that it's equal to the identity. So the claim is that there's a notion of strict triangle where we require just this data. So there's only 9 equations. There's these 3 equations, there's these 3 equations here, and then there's 3 equations L composed with H equals 0 and so on. The claim, we didn't write this down, but I think we kind of agreed that this was going to be true. The claim is that if you have a sufficiently vibrant, let's say, pre-triangulated Digi category, whatever that might be, then any triangle can be expressed in this way.
This is well known, I don't know.
Yeah, that's
Maybe
exactly.
it's illustrated in the group of mine and it's on mine.
Okay, I didn't know it until like, as I said, you guys are going to find that to be a severe lack of knowledge on my own part. There's also an A-infinity version of this, where you require some kind of weak A-infinity structure, which doesn't seem very convenient to use, basically. But where you would, for example, say instead of being equal to the identity, you would give the homotopy between this guy and that identity. Then that has to satisfy itself for the properties and so on. But so now, but I do agree this is definitely has to be well known. So, but now the point is that if we want to really define some category of sections, we need to require this data of a strict triangle in each one of these vertices. So the definition of a section is something where on each edge we give an object in the appropriate category, and at a trivalent vertex, we give a strict triangle. So if you think about it, for example, if some of these objects are 0, I mean, 1 is 0, or no, like B is 0, then you would just say CA equals C or something like that. But there might be different choices of strict triangle that could go with that. But that's some kind of thing. Okay, so now there's a problem of how to define the Fukaya category, and this we haven't done this. So we have just a strategy for defining the Fukaya category. Let me also say that, so this is just, so we're actually reducing to we consider the case of x equals just the complex plane, and a is just a constant. Say a2 or. I guess probably the definition that you would work for any constant fiber category. You can see that's why we're too worried about the problem of transporting stuff from one point to the other. If we just assume that this thing is constant, then the fiber category is always the same. So what's the strategy? The strategy is to, however, we do fix some endpoints. So now in the case where A is a constant sheaf, but we fix some endpoints, that means that our spectral networks, they're not supposed to end at these branch points, but they're supposed to end at our fixed specified set of endpoints. So all those pictures were gone in that situation. So what's the strategy? The strategy is to use some kind of Morse theory. So at some point, Fukaya has a paper about Morse theory done from the Fukaya category sort of viewpoint. So let's just take our graph. So we would like to define the category of steps supported on some given graph. Okay? Say it, but suppose it's a trigonal graph. Okay, so we fix the graph. We fix a graph. We fix maybe some vertical, some upstairs vertices and some downstairs vertices. Then we think of the vertical function as a Morse function. And we try to do sort of Fukaya's version of Morse theory for this graph. And what this amounts to doing basically is, it says we would like to, so the problem here is to define what's the morphism complex between two different objects like that. Okay. So we suppose we have two different objects like that. We want to define the morphism complex. Well, we know that the morphism complex is supposed to be given by intersections of Lagrangians. However, we're not going to intersect this Lagrangian with itself. So what we do is we do this simple version here. Okay, so instead of intersecting this with itself, we actually shift it with a wrapping condition. So we can shift it with a wrapping condition at the top. And then we look at the intersection points of the graph with the shifting graph. Now we put some object on the white one and some object on the blue one, and we take the morphism complexes, the direct sum of the morphism complexes at each of these base points. It's not because this is really coming from Dr. paper about how to do pre-triangulated, how to do pre-infinity structures. Okay, so we can define the morphism complex that way. Then we can define, so we can try to define the A-infinity operation by just successively shifting our object a little bit to the right. completely sure about the wrapping here, but. So when you draw a picture like that, you're going to generate a bunch of little infinitely thin loops, disks in between these objects. And the idea is to use the standard, whatever that may be, the standard way of defining Fukai category, using disk corrections only for these small disks. And so that should define us a Fukai category of objects supported on the graph, an A-infinity category of objects supporting on the graph, but which does not take into account the large loop corrections. Then the hope is what we, as I said, this is completely in progress, so to speak, since we haven't written down any of this. But the hope is that we can then insert the corrections for the big loops into this specific category. So the idea is that this should give us a very specific model into which you can insert the loop corrections. Kind of the problem in defining Fukai categories, I'm not an expert in the field, but as I imagine, the problem in defining Fukai categories is we have this idea that that a holomorphic disk should lead to a correction, and we know kind of what the correction should be basically, but it's not so easy to figure out an actual specific concrete model of a category into which you can plug that correction in, because then you need to show that the corrections combine together to satisfy the A-infinity rule. So as far as I know, you need to really define, before you start inserting the disk corrections, you need to define kind of an underlying non-disk corrected category, but it needs to be completely specific, you know what I'm saying? Otherwise, there's not going to be any way of verifying that the further disk corrections satisfy the A-infinity rule. So anyways, as I said, I'm not claiming at all how to do that. I'm just claiming that this sounds like a strategy which might possibly work. Let's see, so finish it. So that's the kind of basic definitions of the theory. Now what we're doing, as I said, we don't know how to do this anyway, so it's not a big deal that our time is up. What are we trying to do? So we're trying to define a stability condition on this category. Maybe I should say what kind of category do we get? So we're going to get a category over this big K, which is an Novikov field. So what does this mean? This means some kind of power series in powers of t with real coefficients, but I guess the powers of t in a given power series should have a positive, should have a limit equal to plus infinity. Okay? So you can multiply them. And then we have OK.
Excuse me, that's simplistic field of simplicities from the previous idea.
It's a similar, maybe, but I'm not sure whether
But it's not related.
that's a good question, which you should ask Maxime.
I won't do that. I won't do that.
I'm not sure whether that's going to be related or not. That's a good question.
But it doesn't depend on any or definitely, right?
It doesn't depend on any alpha. Now, this is for a different reason. This is in order to take into account the symplectic areas of the disks. The disk correction here is going to multiplied by t to the power a, where a is the area of the disk. And these are reputed to be infinitesimally small, so they're supposed to have a power t to the 0. And so we get this Fukai category over this no problem. Maybe no problem. Now, we would like to have the following thing. So we would like to have a stability condition. So a Bridgeland stability condition on this category, on this Fukai category, over the field. So this means tensoring the Hom objects over the field. And we take the union over all possible graphs. Such that the stable objects of some given phase phi are the spectral networks. For sorry, But we have the spectral curve, which we can think of as being given by a multi-value collection R triple of differential forms. Those differential forms, we can multiply them by a complex angle. And the stable objects of phase 5 should be the spectral networks for this angle times these differentials. You should understand that changes completely the foliation, because remember the foliations were given by taking the real part of the form. So when you turn the angle, that turns the foliation.
Can I ask you a simple question? What is the Grothin group of this category?
That's a good question. Well, in our case, we can actually say what this category is in our case. In the case C is equal to, X equals the complex plane with P1 to Pn, if what they tell me is not mistaken, shall we say, this guy should just be actually the category A n minus 1 tensor A r minus 1. So we're basically just taking a category, we're taking this kind of a Foucault category over the complex plane relative to n different points with coefficients in the fiber category, which is the complex plane relative to r points, the r points of the spectral cover, in this constant case. So in the constant case, this should just be this guy, so I guess, I don't know what it is, but I guess.
No, in fact, I think it's not even A categories from the very beginning, because when you get bracket, you get like series and variable of the B plus 2. That's ugly categories. Like A, but
Yeah. I'm not a big expert on what we're actually supposed to do at this.
I'm just some confusion. I mean, you're talking about the phase of the stability condition, then, so it's somehow, at least you probably want to say that you know how to think about these phases. And then that kind of leads to the question about what the problem is.
working
Yeah.
complex with some lattice.
Yes.
Homology.
Okay, so and what is the latest?
It's some homology of pair, integer homology of pair.
You know, the thing is that to define this category without talking about loop corrections, you can just assume that the graph is a tree spanning these edges. That's not too hard to figure out what the category is going to be from the tree. If the graph is a tree, then we just have a successive collection of, say, we ask for some exact triangle. I'm not completely sure that we really want to wrap stuff around these points. I think that should actually be
If you do Zwicker-Levier models, you don't wrap anything. Special operations Zwicker-Levier, on top of Zwicker-Levier.
You mean if those are the branch ones? You mean?
No, branch points will be still, it will go to...
Yeah, but what if they're like just imposed singular points? I don't think we're going to, if we just sort of impose some boundary conditions at some points. But, you know, I think there's still, I mean, as I said, this is a work in progress. It seems to me that there should be a notion of really stability condition for the reverse Schober. And we need to discuss what the stability condition is at the singular points of the reverse Schober, essentially. Maybe I should just finish by, let me finish by kind of making a comment about that, which is that what's going on here is we're really combining a stability condition in the fiber with a stability condition in the base. And the stability condition in the fiber actually has to take coefficients in the cotangent bundle or the tangent bundle of the base. So the central charge of the fiber has to be thought of as being a vector on the base rather than just as a complex number, essentially. And that's why we have this twisting here. So the slope of an object sort of combines the slope of the object in the fiber with the direction of the vector in the base, essentially. So you might say special Lagrangians where the slope is just constrained as much as possible, is that the graph and the base, these are straight line segments, and the object in the fiber is a stable object in the fiber whose phase corresponds to is equal to the phase theta plus or minus the angle of the edge. So it seems to me that in kind of a fully general version of this theory, we would have a notion of Perver-Schober over the space, and we just have some kind of notion of stability condition on Perver-Schober relative to the base essentially. And that this kind of question about whether it's a graph or not, taking care of that. I'm not an expert on the subject. So let me just comment on where our work is. So we have sorry, I should have drawn some pictures here. It's time to stop. So we kind of have, we're discussing more and more the problem of minimizing the slope. So the essential problem to define stability condition is to define the Harder-Rosino filtration, which means we want to take some object over some general graph. We want to sort of rectify the graph as much as possible to make it so that the total slope of the object on the fiber plus the object on the edge becomes as small as possible on each edge. The maximum, the supremum of the total slope of the graph becomes as small as possible. And roughly speaking, the idea is that if we try to do that, the place where we get blocked from decreasing that slope even more is going to be a place where there should be a sub-object of that maximal slope, a stable sub-object of that maximal slope, will sort of appear at that point. I cannot say that we have a viable strategy for doing that so far, though you have some idea. And we also have, which is maybe the subject of a different talk, we have some pictures of the case where there's just 6 points, so this case here, basically. We can draw, let me just see why this might be complicated. You can draw spectral networks for these points where you can sort of do something like that. That might be an example. You can just draw spectral networks in a strange way. And we actually have a strategy for drawing a picture of all the spectral networks, in that case of 6 regularly spaced points. But maybe I'll stop.
We have time for one question.
Sounds strange that if you, in case your theta by 2 pi, then the set of stable objects will not change.
But that's just shifting. That's just a shift of the. I think that's true for any stability condition.
I mean, still in this definition, it should be sensible to things like that. As you explained, it is not sensible.
But that's true for any stability condition. That's just the shift of the stable objects, or a shift of the stable object.
But probably what you say is that you should somehow decompose this spectral networks into stable objects for different shapes. I don't see how you.
No, the spectral networks are not really, don't really have any shifts in it because we've labeled the edges by these objects A, B, C, which are stable objects in the fiber category. So when I said that the fiber category was
the conditions that they
well, when I said the fiber category had just 3 objects that looked like that wasn't true in the sense that we all have shifts these objects. So if you shift everything, but if we assume that, well, when we're talking about a spectral network, we're talking about a spectral network with label, or these objects contained in a certain interval length pi. Basically, we're not allowing we're not allowed to say take an ij guy and make a shift of the jk guy. That's not allowed.
So you're saying that the definition is more complicated than
And I remember when actually they didn't talk about shifts or anything, because they didn't talk about a fiber category fiber. So I mean, you might say it's labeled by it's an object in the heart of the structure on the fiber, basically. And if you rotate by 2 pi or even pi, then you'll get the same spectral network, but labeled by objects in the shift of that part.
All right, so let's thank God for the last call.
Thank you.